Hi, this is Tim, and welcome to another episode of Talks with Tim. Or at least that's what Jake Hall over on LinkedIn wants to call it. And for that entry, he is in the running for a PLC Tools SIM-ALP2 analog simulator. Some quick details on that. Between now and the 9th episode, we are going to be taking submissions for what you think we ought to name this podcast. And then we're going to put the best entries out for a vote. And on the 10th episode, we are going to award an analog simulator to the winner and give some other exciting details. But today, we're going to talk about binary numbers. And this one I need a lot of feedback on because I really want to show you some props with some lines, circles, and arrows and everything to explain this. But can I describe clearly binary numbers over a podcast? So in this one, I'm not going to show you anything. I am going to describe what I'm drawing on a piece of paper so you can follow me along. Give me your feedback on this. Tell me what I can do better or whether this was helpful, because this is going to kind of help us determine, one, what we can do with the podcast and whether they're worthwhile for some of the more in-depth topics. So if you've been in any programming industry for very long, you have probably seen the saying, there's 10 types of people in the world. Those who understand binary and those who don't. In fact, we have a t-shirt that says that. I should have worn that t-shirt today, but I didn't. Okay, well, it's a podcast. You can't see it, but I'll put a link in the description where you can see the t-shirt. But what does it actually mean? And that's what we're going to talk about today. And we're actually going to start by talking about the base 10 numbering system, because I find a lot of people don't fully understand it, even though obviously it's what we use every day. But if I tell you that, we use a base 10 numbering system, and I ask you, what are the 10 numbers? Chances are you're going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But that's not actually the numbers. Amber, I drove her insane when the kids were like in kindergarten, first grade, because they'd come home and tell me they knew how to count now. And that's what they would do is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'd ask them, well, where's the zero at? And they would look completely stumped. Now, you could actually go on a fascinating rabbit trail about the number zero, because it's fascinating that it didn't exist for a long time. And in a lot of societies, it hasn't existed until real modern times. I mean, we're talking like in, Greek times, there was nothing to represent zero. In fact, no, I have not done a lot of research on this. I just did some quick looking, but Aristotle even dismissed zero because you couldn't divide by it, so it must not have a lot of meaning. But it has a lot of meaning, and it has an important meaning if we're trying to understand how to convert between binary, decimal, and things like that. So in a base 10 numbering system, the numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That 0 has a lot of power in understanding this. Now let's go old school and do some basic addition in the base 10 system. So I'm going to describe what I'm doing, and you can follow along, or maybe you can visualize it. I'm going to write the number 7. And then right beneath it, I'm going to write the number 3. And then to the left of the 3, I'm going to put a plus sign. And then I'm going to draw a line underneath the plus and the 3. And this should look like a very elementary school math equation of 7 plus 3, which everybody's probably thinking, well, yeah, Tim, that's 10. But okay, let's actually slow down a little bit and let's break this down. Because if we're in a base 10 numbering system, then we only had numbers 0 through 9. And so 7 plus 3 is going to make us roll over from a 9 back to a 0. And when we roll over, just imagine those old school odometers, like before we had digital odometers. You know how they kind of roll around? And okay, we get to 9, and then the odometer rolls around to 0, and as it does, it drags that 10th place up to a 1, and that's how we actually get to 10. Well, that's what we're going to do here, is we're going to roll over and we are going to end up with that 0 that we're going to put beneath the 3. And then that rollover, or we may call it a carryover, is going to be that 1. And we'll put it kind of above and to the left of the 7. And now we're going to be back to that power of 0 that I can't stress enough that we need to teach more of. Is to the left of that 7, there is an invisible 0. And to the left of that 3, which probably your plus sign's kind of in the way, or at least mine is if you made it really neat, there's also an invisible 0. Because we can have a gazillion zeros to the left of a number, and it's not going to change its value. But now we have 1 plus 0 plus 0 is going to equal 1. And yes, I just took a really insanely long way around to come up with 7 plus 3 equals 10. But let's do it one more time. Let's write an 8. And then underneath it, I'm going to put a 5. Then to the left of the 5, I'm going to put a plus sign. And then I'm going to draw a line underneath the plus sign and the 5. Looks like old school, 8 plus 5. 8 plus 5, you're probably like, I can do that in my head, it's 13. But again, let's just slow down a little bit. Because 8 plus 5, yeah, we're going to roll over. We're going to put that 1 over there, but actually 8 plus 5 is 3 with 1 rolled over or carried over, whichever one you like. And then we have those invisible zeros again. We have a 0 beside the 8, and we have a 0 beside of the 5. I'm sorry, to the left of both of those. And 1 plus 0 is going to equal 1. And 1, 3, or 13 is our answer. Now let's talk about binary, or a base 2 numbering system. In this case, we have 2 options, and they're not 1 and 2. They are 0 and 1. This concept is pretty easy for most people to get because it's very similar to a discrete input or output on a PLC or any flag that's kind of go, no go. You have 0 or you have 1. You have true or you have false. So based off of that, really easily, we can represent 0 because that's 0. And we can represent 1 because that is 1. But now let's add 1 binary plus 1 binary. So on my sheet of paper, I'm going to write a 1, and I'm going to put a B just to represent that it's binary. And then below it, I'm going to put another 1B. Then to the left of the lower 1B, I'm going to put a plus sign. And then I'm going to put a line underneath the plus 1B. Similar to our old school math, but now it's 1 binary plus 1 binary. Now let's visualize that old school odometer. But now instead of us having 0 through 9 on our little dial that's turning on the odometer, we only have 0 and 1. So if we go above that 1, we have to carry the number over to the next column. So 1 plus 1, all right, that is going to roll over, and we're going to end up with 0. And we're going to carry over our 1. And no matter what numbering system you're in, you can have a gazillion zeros to the left. I shouldn't say whatever number system you're in because somebody's going to call me out on that. In most numbering systems, you can have a gazillion zeros to the left. So we have an invisible 0 to the left of our 1 in both columns. And now 1 plus 0 equals 1. And our answer is 1, 0 binary. Now mentally, if we're thinking base 10, because usually when you look at numbers you're going to say 10. It's not actually 10. It is 1, 0 in binary. So 1 plus 1 binary equals 1, 0 in binary. And that's how we come up with the concept of there's 10 types of people in the world. Those who understand binary and those who don't. Now let's take it a step further though, so that we can actually begin to understand more than just what the t-shirt means. is let's just randomly write down another number. Now we're in binary, so our number can only consist of zeros and ones. And I'm going to write down 1, 0, 0, 1, 1. And then beneath it, I am going to write 1, 1, 0, 1, 0. And to the left of that number that's written, I'm going to put a plus sign, and I'm going to draw a line underneath it. So you should end up with 1, 0, 0, 1, 1 plus 1, 1, 0, 1, 0. All right, let's do the math. And again, you got to remember you're in binary. So your numbering system, you only have a 0 and 1, and after that, you got to roll over to the next digit. So 1 plus 0 will be 1. That was pretty easy. So now we have 1 plus 1. All right, well, we rolled over with that. So our answer is 0, and we're going to carry over a 1. Next, we'll have that 1 that we just carried over plus 0 plus 0 equals 1. Next, we have 0 plus 1, which will be 1. And finally, we have 1 plus 1, which is going to be 0 with 1 carried over. And then we have an invisible 0 to the left of both of our 1s at the beginning of those numbers. And then 1 plus 0 equals 1. That's a lot of 1s and 0s. And so now I need to go on a quick rabbit trail with instructors and say that you should not have your students do any more than what I have just done on paper to understand binary. Because now we're going to use the Windows calculator to start to understand what this means and how we can relate what we're seeing in these 1s and 0s to 1 base 10, and also how we can manipulate them in our Windows calculator. So open up your calculator, and by default, if you look in the top left of your calculator, you're going to see it says standard. If you hit the dash, dash, dash to the left of that standard, then we also have a programmer calculator. And that's going to give us some really cool programming features. And you'll see that in addition to our normal 0 that's showing whatever our calculation answer was, below it we have hex, dec, oct, and binary. And that's hexadecimal, decimal, octal, and binary. And you can highlight them. So click on the hex now. You're going to see a blue vertical line to the left of the hex. Or we can select decimal. And now the blue line moves. Octal, blue line moves to it. And finally binary. And the blue line moves to it. And also notice, like when you just selected binary, all the numbers went away except for 0 and 1. And if you go back up to octal, then you only have 0 through 7 because that's all the numbers that there is in an octal numbering system. Decimal, you have 0 through 9. You know, and that's kind of the funny thing. As much issue as I have getting people to understand the concept of 0 with the base 10 system, if you look on a calculator, there's only 0 through 9. There's not a 10 button. And finally, if we go to hex, you notice on the left side, beside your numeric numbers you're used to, you have A through F, because that is part of the hexadecimal numbering system, which probably we should cover in another podcast. But for now, let's highlight bin or binary. That gets us back down there. And let's type our number in. So we had 1, 0, 0, 1, 1. And then let's hit the plus sign, just like our equation says. And then let's type in 1, 1, 0, 1, 0, and hit the equals key. And you're going to come up with the exact same answer I just came up with, 1, 0, 1, 1, 0, 1. Also, one of the best features of the Windows calculator in programming mode is if we look up now, we can see that this decimal value is 45. Now let's take this down a little bit more of a rabbit hole. Let's go back, let's in fact just hit your escape key, So you got zeros again. Make sure you have binary highlighted. And enter that first value again, 1, 0, 0, 1, 1. And look, that decimal number is 19. Just write it down somewhere to the right of that number. And then let's do the other number. So hit the escape key to zero everything out and enter it, 1, 1, 0, 1, 0. And in decimal, that's going to be 26. And now let's highlight decimal. Or you could go to your standard calculator and type 19 plus 26. And that's going to equal that same 45 that we saw in that decimal value. So doing math in decimal or hex or octal or binary, we'll end up coming up with the exact same number. Okay, now let's talk a little about binary to decimal conversions. And for this, I've got my paper, what do you call it, tallways? What is that? Portrait? I've got it portrait, and I'm gonna write down the left column. I'm gonna write at the top left, I'm gonna write 0, and then directly below it, I'm gonna write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And this will be a 16-bit value. So we already know that our first position, or position 0, we can represent 0 or 1. So it has a value of 1. So beside of that 0 at the top, to the right of it, I'm going to put equals 1. And we've already figured out that the 1 position, or 1, 0 in binary, equals 2. So I'm going to put equals 2 beside of that 1. Now, let's use our programmer calculator just to get a reality check on what might be the value of position 2 of binary. So if we click on our binary and enter 1, 0, 0, then we can look up at our decimal value and it's going to be 4. Then we have the third position. Well, let's go ahead and escape to clear out what we have in our calculator and put in 1, 0, 0, 0. And now our decimal value is equal to 8. And hopefully now you're starting to see a pattern. The 0 position is going to be a value of 1. The 1 position, 2. 2 position, 4. 3 position, 8. So they double each time. So the 4 position is going to be 16. The 5 position is going to be 32. The 6 position is going to be 64. The 7 position is going to be 128. The 8 position is going to be 256. The 9 position is going to be 512. The 10 position is going to be 1024. The 11 position is going to be 2048. The 12 position is going to be 4096. The 13 position is going to be 8192. The 14 position is going to be 16,384. Now let's pause on that 15 position. We're going to come back to it. Also on another rabbit trail about my kids. You know, my kids can actually do this. I've had them doing binary since they were like 6 years old and they didn't realize it. But as soon as their minds could almost do some multiplication, I would be like, well, what happens if we double 1? And they'd be like, 2. What happens if they double 2? They'd be like, 4. What happens if they double 4? They'd be like, 8. And yeah, they could be thinking real, if they would think really hard, they could be like 16,384. So even today, I could ask them to multiply through this really fast, and it's just ingrained in their memory. So these are numbers that probably you should become familiar with. But okay, now we have the values of them. So let's go back to our previous sheet and look at it. So I'm going to set a sheet aside that I just wrote all those on so I can refer back to it easily. And our first value which we know now was 19, but it was in binary 1, 0, 0, 1, 1. Now, when you're looking at binary, the 0 position is that right-hand one. So directly below it, I'm going to put the value off my cheat sheet. So we have 5 positions. The far right one, the value will be 1. The next one to the left will be 2. The next one will be 4. The next one will be 8. And finally, we're going to have 16. And I'm going to put a line underneath it, but we're not actually going to do any addition here, because we're going to do multiplication down these. So working off of the right side, 1 times 1 is going to be 1. I'm going to put a really small plus sign to the left of that 1 and go to the next column. We have 1 times 2, and that's going to be 2. And then I put another little small plus sign. Next column, we have 0 times 4, and I'll put another little plus sign. And then we have, oh, I'm sorry, I didn't tell you the answer. 0 times 4 is going to be 0. And a little plus sign. And then 0 times 8 is going to be 0. And finally, we have 1 times 16. It's going to be 16. So in the end, we end up with 16 plus 0 plus 2 plus 1. And that is going to equal 19, which is the same value that we had figured out in our scientific calculator. So you didn't realize it, but you just did a binary to decimal conversion by doing that. So let's take our other number here, which was 11010. So I'm going to write that down here. 11010. And that far right position, according to my cheat sheet, is a value of 1. So directly beneath it, I'm going to put a value of 1. The next one to the left is a 2. The next one to the left is a 4. The next one to the left is an 8. And the next one to the left is a 16. And I'm drawing a line underneath it. And we're going to do the same multiplication. We're going to go 0 times 1 is going to be 0. I'm going to put a small plus sign to the left of it. And then 1 times 2 is going to be 3. And I'll put a small plus sign to the left of it. 0 times 4 will be 0. Small plus sign to the left of it. 1 times 8 is going to be 8. Small plus sign to the left of it. And 1 times 16 is going to be 16. So now let's add all of these together. So 16 plus 8 is going to be 24. And 24 plus 2 is going to be 26. And that is what we determined it was in the scientific calculator. So now you know how to do binary to decimal conversions. We can also do the opposite though. So let's take another sheet of paper and let's write down 1, 2, 3, 4, 5. Now we're going to convert 1, 2, 3, 4, 5 decimal to a binary number. And to do that, we actually do the exact same thing you did in The Price is Right. You want to find the number that is the closest to your number without going over. So if I look down my cheat sheet, I see bit number 13 was 8192 and bit number 14, 16384. So the closest bit without going over is going to be bit 13 at 8192. For now, I'm just going to make a note out here to the left that says 13. So I remember which bit it was. And then we're going to subtract 8192 from 1, 2, 3, 4, 5. So directly beneath the 2, we're going to put the 8. Directly beneath the 3, we're going to put the 1. Directly beneath the 4, we're going to put the 9. And directly beneath the 5, we're going to put the 2. And I'm going to put a minus sign to the left of the 8. And underneath all that, I am going to put a line. So it looks like a longer old school subtraction problem. 5 minus 2 is going to be 3. 4 minus 9, we're going to have to go borrow, and I don't borrow like they do now. I just borrow a 1 from that 3 beside of it and make it a 2, which means 14 minus 9 is going to be 5. And then 2 minus 1 is going to be 1. And then 12 minus 8 is going to be 4. So we're left with 4153. I should probably check that because, yeah, this is not a test. Let's make sure. 1, 2, 3, 4, 5 minus 8192 equals, yeah, 4153. So now we're going to go back to our cheat sheet over here and we're going to find the largest number without going over 4153. And that is going to be bit 12 at 4096. So I am going to make a note of bit 12 over here, just kind of in a little scratch area. And then beneath the 4153, I'm going to put 4096. And it should line up really nicely underneath it. We put a subtract sign to the left of the 4096 and we draw a line under it. So now, can't do 3 minus 6, so I'm going to go borrow 1 from that 5, make it a 4, and 13 minus 6 is going to be 7. And I can't do 4 minus 9, so I'm going to borrow a 1 from that 1 to the left of it, put a 0 there, and now 14 minus 9 is going to be 5. 0 minus 0 will be 0, and 4 minus 4 will be 0. So my answer is 57. So now we're going to go to our sheet again and find the highest number without going over, and it's going to be bit 5 at a value of 32. So I'm going to make a 5 over in my little scratch area, and I'm going to put directly beneath the 57, I'm going to put 32. And to the left of the 32, I'll put a subtract. And I'm going to put a line underneath the 32. 7 minus 2 is 5. And 5 minus 3 is 2, or 25. And now we're going to find the next biggest number without going over, which is going to be bit 4 at 16. And I'm going to write that 4 in my little scratch area. And then I am going to put 16 underneath the 25, and 5 minus 6, can't do it, so I gotta go borrow from that 2, make it a 1, and 15 minus 6 is gonna be 9, and 1 minus 1 is gonna be 0, so we're left with 9. So now we'll go and find the closest number to 9 without going over, and it is gonna be bit 3 with a value of 8. In my little scratch area, I'm gonna put a 3, and I'm gonna put an 8 directly underneath the 9. Put a minus to the left of the 8, draw a line underneath it, and 8 minus 9 is going to equal 1. Now we're going to go back and we're going to find the value closest to 1 without going over, and it is going to be bit 0. So I'm going to write that 0 down in my little scratch area, and then beneath my 1, I'm going to put a 1. To the left of it, I'm going to put a minus. I'm going to draw a line underneath it. And 1 minus 1 is going to be 0. Okay, so we end up with a lot of scratch, subtraction, and crazy things. And we ended up with some numbers that we jotted down. 13, 12, 5, 4, 3, and 0. So now we're going to take those numbers, and wherever one of those numbers are, we're going to put a 1. And we're going to start from the lowest one. So bit 0 is written down. So on the right side where I'm going to put my result, I'm going to put a 1 in that place for bit 0. Okay, and then 1 and 2 were not on our jotted list. So they're going to be 0s. So to the left of the 1, I'm going to put a 0 and another 0. And then bit 3 we used. So we're going to put a 1 there. Bit 4 was used. So we're going to put a 1 there. Bit 5 was used. We're going to put a 1 there. Now 6 wasn't used, so we'll put a 0. 7 wasn't used, so we'll put a 0. 8 wasn't used, so we'll put a 0. 9 wasn't used, so we'll put a 0. 10 wasn't used, so we'll put a 0. 11 wasn't used, so we'll put a 0. 12 was used, so we'll put a 1. And 13 was used, so we'll put a 1. And then bit 14 and 15 were not needed, which means they were zeros. So your answer would be 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 1. That's a lot of ones and zeros, but that's why we got this cool Windows programming calculator. Is let's go over to it, make sure your value's cleared out, highlight binary so you have a blue line to the left of it, and let's type that in. 1, 1, 0, 0, 0, 0, 0, 0, that was 6 zeros, and then 1, 1, 1, that was 3 ones, 0, 0, 1. And if we look at our decimal value, we get 1, 2, 3, 4, 5. And I apologize for how long that was because I really didn't think that it was going to take that much complexity. I should have made it 1, 2, 3, 4. But anyway, there you go. You just converted a decimal number to a binary number. Now, again, instructors, do not have your students sit here and write out 50 different conversions. That's not the point of this. The point of this is just a quick exercise to say, hey, here's what a binary number is. This is what they mean when they say 1, 0 in binary equals 2 in decimal. And yeah, here's what all those ones and zeros that you see mean. But yeah, there's no need to really drag this out too far because yeah, well, that's why we have the Windows calculator now. But anyway, this was a podcast suggestion. So what do you think? Was I able to describe binary and binary to decimal conversions and conversions from decimal to binary without any props? Let me know what you think in the comments. And again, put your submission in for what we should name this podcast. We are giving away one of the PLC Tools Sim ALP2 analog simulators as a prize. Till next time. I just realized I didn't talk about bit 15. I said, let's wait to talk about it, but I never talked about it. So quick answer, bit 15's purpose is dependent on whether you have a signed or an unsigned integer. And that's enough that I think probably we should cover it in another episode. But real quick is if you're dealing with a signed integer, then that bit 15 is going to be the sign. So if it's a 0, it's going to be a positive number. If it's a 1, it's going to be a negative number. If you're dealing with an unsigned integer, then bit 15 is just another multiplied by 2. So we would take 32,768 and multiply it by 2 to give us 65,536. And note, if we have a signed integer, our maximum value then is only half. So we're going to be at that 32,768 number. But there's a lot of other things we probably need to talk about that sign and mainly manipulation of data. Enough that I think I'm not going to go into that in this podcast. But I did want to throw that really quickly out there. Hi, this is Tim.
And this is Amber of TW Controls. We run the automation store. Hey, thanks for finding our channel.
Here's a playlist with some similar videos.
And YouTube thinks you'll like this video.
Please like our video and subscribe to our channel.
And if our videos have helped you make some money and you're not using our products, please consider supporting us on Patreon.
Till next time.
See ya!